called line integrals. And of course, just as we saw with partial derivatives, when we look at functions of two or more variables, there's more possibilities. There's different variables, so you can talk about derivatives with respect to any one of the variables, and then you can iterate or compose the derivatives operators in any number of ways. So there's lots of different derivatives of different orders and so on. And similarly with integration, because there's more than one variable, because the domain has got a dimension greater than one, so single function variables is just a one-dimensional domain. And to integrate such a function, you track across a portion of that domain, but in a one-dimensional space, a portion of the domain is quite simple. It's just the basic type of portion is just an interval between two limits on the number line of the one-dimensional domain. But with functions of two or more variables, immediately there's more possibilities. So for a function of two variables, the domain of the function is now a two-dimensional plane. Okay? And so if you want to do some kind of integral, some kind of summing up of the values of the function, or some kind of accumulation of the values of the function, because the domain is two-dimensional, there's more possibilities about what you can talk about. The first type of integral we're going to talk about is when we integrate. Let's draw a couple of sketches here, just suggested sketches here. So thinking of our function of two variables. Here's the x, y, z plane. And here's the surface z equals f of x, y. The two basic types of integrals for a function of two variables like this, well, we can have so-called path or line integrals. So that's where we have a path in the domain, say some curve C. So that curve C is in the xy plane. C is a curve in the xy plane. And we can integrate the function along that curve. So we can do some kind of, we can perform, so we'll talk in detail about it now shortly, we can perform some kind of integral integrating over the curve C, integrating the function f of x, y. And we'll say a bit more about what kind of differentials here or are the options there in a moment. That's one kind of integral. Another kind of integral is where you're not integrating along a curve in the xy plane, but you're integrating across or over a two-dimensional region within the plane. So you could have, in principle, some arbitrarily shaped region here. So that's a region R, a two-dimensional region, as opposed to just a curve, but actual two-dimensional portion of the domain. So 2D region R in the xy plane. And we can integrate over this. So integrating along the curve in some sense, which we'll make a bit more precise, but in some sense picks up the behavior of the function f over the curve or along the curve and sums it up in some way. Integrating across a region, again, you can project upwards, and this region, if you project upwards, it will look something, well, it will have some complicated shape, maybe up on the surface itself. It should kind of look like a look to that. But of course, it might be the surface could be bending and twisted and that. So the two-dimensional region R you have in the plane, when you lift it up the surface, it could have a kind of distorted shape. So you get this kind of, well, it's kind of like a cylinder in some ways, except it could have an arbitrarily shaped bottom portion, R. It's got straight vertical walls, and then its top, and the top of the cylindrical region is this region R projected up onto the surface. So that could be has a different shape again. But we can integrate over this to get integrals like, and again, when we come to look at them in detail, we'll explain exactly what they mean in detail. But this would look something like it's a double integral. So the double integral, because we're integrating across a two-dimensional region, R, and we're integrating as of x, y, and typically we have something like dx, dy. And this actually is exactly, we can say exactly what the interpretation of this is. This is exactly the volume of the cylindrical region. Cylindrical region between surface defined by the function and the region R. That kind of cylindrical portion of three-dimensional space there is bounded above by the surface and below by the region R, plane straight vertical walls. We are going to talk about a double integral or a multiple integral, which the notation vaguely looks like that. Double integral over R of the function over x and y, and this is going to be exactly the volume of that shift. Okay. Then, of course, if you increase the number of variables, if you have a function defined on 3 variables, that means it's defined in portions of our familiar three-dimensional space, then you would integrate the function in general. You could integrate it across a volume of three-dimensional space. So the function takes various values, three-dimensional space, then you could integrate it across a volume. You could imagine, say, a temperature function. A function which gives the exact temperature of every point in this three-dimensional volume where we are. And then we could integrate that function over sub-volumes of this room, say, integrate it over sub-volumes, and that would sum up all the temperatures in that volume. So this is the general kind of looking ahead at a few things that are going to come. And just quickly drawing a few kind of suggestive diagrams. So we'll make it a bit more exact now when we get to the notes. So switch back to the notes. This is page 23. Okay, so the first type of integral we're going to look at are called line integrals or path integrals, they're also sometimes called, or sometimes called integrating the function over a curve. And we're going to look at the two-dimensional case, so for functions of 2 variables. And then the kind of things we're going to be integrating are, you see, because there's 2 variables, we can integrate with respect to x or with respect to y. X and y are the 2 basis directions for the domain. So the kind of things we'll be integrating are these things of the form L here. So L is called a linear differential form. So it's a linear combination of the differentials dx and dy. Multiplying dx, you can have any function of x and y. And multiplying dy, you have another function of x. So we have a p x of y times dx and a q x of y, q of x and y, and multiplying dy. So from the one-dimensional case, our basic picture of an integral is like this object I here, integrating from a to b, summing up the values of the function f along that interval from a to b. So we're going to do, we're going to generalize this to functions of 2 variables. So they're going to look kind of similar, except, as I mentioned, when the domain was one-dimensional, you've got a point A in the domain on the number line, another point B. There's really only one way that you can progress from A to B. You have to move along the number line. Now, there are different ways you can do it. You can move along at different speeds, and maybe you can backtrack over yourself a bit and move forward, and maybe backtrack a bit again. But so you can alter the speed at which you go along the path, and you can reverse direction. But essentially, there's only one path from a point A on the number line to another point B. You just have to go along the one-dimensional number line until you hit the other point. There's very little choice. All you can vary is your speed, and then you can change direction a few times. If you have to start at A and then B, really, there's only one way to get there. But of course, when you're in the two-dimensional domain of functions like this P and Q here, you've got 2 points in the domain. Suddenly, there's an enormous, there's an infinite choice of different routes you can take between 2 points. I'm going to walk from here to the door. I can go in a straight line. I can follow a curved path. And up the stairs there, across the back, down the stairs there. Okay, let's think in 3 dimensions. Even just along the two-dimensional plane of the floor, there's an infinite number of paths I can take, and they're all distinct and moving through different points along those paths. So it's not enough simply to say integrate this linear differential form from a point A to a point B. You have to fully specify the curve. Okay? All those different choices I talked about for the one-dimensional case of varying speed and backtracking, I think they all cancel out, and they all give rise to the same value of an integral r. Whereas in functions of 2 dimensions, we're going to observe that really in general, if I'm integrating from a start point to an end point, it makes a difference which path I move along. In general, integrating along a different path will give a different answer. So let's straight away look at an example. I'm going to write through on the notes anyhow. Although I think all the steps are there in the notes. It just helps me to explain it. So we're going to integrate this linear differential form. So we're given a particular linear differential form here. So it's 10x squared y dx plus 3x plus 2y, 3x plus 2y dy. And we're integrating along the curve C, where C goes from the origin to the point 1, 1 along the curve specified by y equals x squared. If I just draw the xy plane, I've got the origin 0, 0, the point 1, 1, and I'm moving along the x squared curve. So I'm moving along this y equals x squared curve. So this is my curve C. And there's a direction attached to it. So it's from the origin to the point 1, 1. I mean, the curve y equals x squared would be defined across the whole of the x-axis, but we're just talking about this little segment of it from the origin to the point 1, 1. We'll say I is equal to this. Now, how we come to actually evaluate I, to evaluate the integral? Well, we want to make use of, you just have to do a couple of steps or apply a principle similar to the partial differentiation case, and then make use of all the normal one-dimensional integration theory of the. So the way to do this is to use the definition of C. So use the definition of C to translate I into just one of the variables. So let's say into x. So we'll aim to replace the y's and dy's with equivalent expressions in x. Okay, so that's the similar to how we had that one principle for taking partial derivatives, and if you're differentiating with respect to one variable, you treat the other variables as a constant, and then just apply the normal rules of differentiation that we have in one variable case. So to take these path integrals, the idea will be to look at the definition of the path of the curve that we're integrating along, and try and use that to transform the two variable thing, the original integral I, transform it and translate it until it looks just like a one variable integral, which we already know how to do. So along C, y is equal to x squared, so we can just do simple substitution to get rid of the variables y in the original integral. But then we should look at how the differentials are related. And there we kind of use a chain rule principles to say that for the differential dy, if y is defined as x squared, then the differential dy is going to be 2x dx. 2x dx. So we want to take the differential of y. If y is defined as x squared, we want to take the differential of x squared. We need to apply the chain rule. So it's not as simple. It's not just the variable x there on its own. It's a function of x. So it's going to be 2 times x dx. So you differentiate the function of x that's there, and then you have the differential dx occurring as an extra factor here. Okay. But we can use these now to look at I and translate everything to x. So we have 10x squared y, but that will become 10x to the power of 4, and that's multiplied by dx. And then we've got a 3x plus 2y, but that will be 2x squared. And that's multiplied by dy, which is now 2x dx. So that looks like we've succeeded in translating everything into x. Except I haven't said anything about what the limits of integration are. Now we're going along this curve from the origin to the point 1, 1. But we translated everything into x, and we just have to look at, well, what's happening to the variable x in that respect. Well, x is starting at 0, and it progresses to 1. Okay, this is what the variable x is doing in this integral. And the movement of y will be taken care of by the fact that we've made the substitutions, y equals x squared and dy equals 2x dx. So we're integrating from 0 to 1. So this now looks like, something that is much more familiar and much less scary. We've got in total 10x4 plus, 10x4 plus 4x cubed plus 6x squared and dx. So we're integrating all of that. That's just now a one-dimensional integral. We just evaluate in the usual way. Just done in the notes, and it comes out as 5, I think. And integrate to 2x to the 5 plus x to the 4 plus 2x cubed. Evaluate that 0 and 1, just 2 plus 1 is 2. Now we'll return to this example in a moment, and we'll integrate it along a different curve between the origin and the endpoint 1, 1, and we'll make an observation there about how the value is not preserved. Okay, so that was example 1.14. So then go on and have a look at theorem 1.4 on the following page, on page 24, which lists some properties of integrals. Okay, so these are some basic properties of line integrals. Basic properties of line integrals that we're going to make use of. Okay, and we can use these to help us evaluate line integrals. And they also bear, yeah, I think most of them are just generalization. In fact, they all are. They're all just generalizations of similar looking properties of one-dimensional integrals. Okay. So the first off is just remember that integration is still a linear operator. So if you take the integral, well, as is written there, the integral of a sum. So this, if you're looking at this linear differential form, which is the sum of two different parts, a dx part and a dy part, you can split it up into the sum of the two integrals on their own. Okay, and then just use similar principles to evaluate them that we just used an example. I was careful. So integration is a linear operator. This is going to be true of all the integrals we looked at. It's general feature of integration. I was careful when I sketched the curve C, y equals x squared in the diagram there. I was careful to add an arrow to it to indicate the direction of the curve, because in integration, part of the specification is that we're integrating from this start point to this end point. Okay? So the direction of travel along the curve is important. And there's a nice relationship between integrating along a curve in one direction and integrating along it in the reverse direction. So in this next equation 142 there, C prime refers to the same curve C, but traversed in the opposite direction. Okay, so starting at the end point of C and finishing at the beginning point of C. That's the curve C prime. It's just the curve C in reverse. And integrating the same linear differential form over C and C prime, they're simply the negative on each other. Okay? So integrating over C is the same as minus integrating over C prime. The third property is about splitting up the curve. Okay? Do that sketch to go along with this third property. Curve 1.4, part 3. If we're integrating, says this up there, A to C. So if we're integrating along some curve from A to C, okay, so we could be considering this object, integration along a curve L, integrating a linear differential form L along some curve from a start point A to an end point C. If B would be any intermediate point along there, then we can split the integration up if we want. And we'll be looking at an example of that. Now we can split it up into, so one separate object we can integrate from A to B, just along the same curve, and then separately integrate from B to C, integrating L, but then still along the same curve. And then we can simply add together those integrals to get the original integral. So that's very similar to compare with the one-dimensional property. If you've got a function f of x, and you're integrating f of x dx, just in a one-dimensional sense, from A to C, you're familiar with the property that if you want, you can introduce an intermediate point B, and firstly you can integrate from A to B, f of x dx, and separately integrate B to C, f of x dx, and add the results together to get the original. And also for part 2, where we integrated along a curve in reverse. That again is just a generalization of the two-dimensional. In fact, I don't need a second picture, it's the same picture. We're integrating from b to a of f of x dx is minus the integral from a to b of f of x dx. If we integrate from left to right in the usual in the positive direction of the x-axis, we go in the opposite direction, then we pick up the negative of going in the positive direction. So changing direction in the one-dimensional case changes the sign of the integral, and that's exactly true in the two-dimensional case, and for half integrals in more than two variables, that changing the direction of travel along the same curve simply changes the sign of the integral. Okay. Okay, so let's look at another example then, example 1.15. So you'll notice here that we're using the same linear differential as before. And indeed, we're using the same start point and end point as before. Going from the origin to the point 1, 1. But this time we're going along a different curve. So A to D and D to B. D to B. So we've just got this other point D here, which is the point 1, 0. And we're going to go along, label the origin A, and the point 1, 1 there is B. So we're going to do the integral along C of L. So it's the same L as before. So as an example 1.14, where C is the curve formed by the two straight line segments. And this is written in the notes, really, just reading it for myself, really. It's the two straight line segments, AD and DB. First you go A to D, and then you continue on D to B in those horizontal and vertical lines. So straight away we'll employ that third property about splitting curves up at intermediate points. So D is the intermediate point along this curve C. And it makes sense to break the curve into those two portions, okay? Because one is going parallel to the x-axis and the other one's going parallel to the y-axis. So integrating with respect to x and y, it will make sense to consider those separately. Okay? So using property 3 from theorem 2.4, theorem 1.4, you can say the integral along C of L is the integral from A to D of L plus the integral along dB L. Okay, so here these subscripts AD and dB now are referring to the straight line paths. Not just any old path from A to D or D to B, but the straight line paths indicated in the diagram. So we'll consider both of these integrals separately, because the two curves, A to D and D to B, have very different properties in terms of the x and y, and they both simplify in slightly different ways. Okay. So first of all, we'll note that along AD, y has this constant value of 0 as you move along the curve A to D. It's just moving along the x-axis. Yeah. So dy is equal to 0 also, because y is not changing. So the differential, which is in some way tracking kind of infinitesimal small changes in y, that's the some kind of limiting object of changes in the y variable. But if y isn't changing at all, if y is just held at a constant value, then the differential dy will be 0 along the curve AD. Okay? And x progresses from 0 to 1 along AD. So that is going to simplify the integral somewhat. The integral along AD of L is going to be the integral. So now we'll look at exactly what L is: 10x squared 1 dx plus 3x plus 2y dy. We're going along the curve A to D. But we've identified these aspects of the curve A to D. Y is always 0. So well, if y is 0, then this part of the integral isn't going to contribute anything because it's got a factor of 1. So summing up the contributions of this part to the integral, it's got a factor of 0 in it, so it's not going to contribute at all. And similarly, this second part, well, this is with respect to the differential dy. But all the way along the curve A to D, dy is equal to 0. Okay? So this part isn't going to contribute anything else. Okay? So the whole thing comes out to 0. Okay? As both terms are 0 along AD. Both terms are 0 along AD. So that really simplifies it. It's got 0 contribution along A to D. So next we will look at D to B to figure out the second contribution to the overall integral. So along D to B, so you just look at what the curve is and just pick out the behavior. Now, it's a straight line parallel to one of the axes, so it's relatively straightforward to describe what's going on. Here now, x is always fixed at a constant value. All the way along the curve D to B, x is held fixed at this value x equals 1. And because it's held constant, the differential dx is equal to 0 as well. Okay, because x, the variable x, isn't changing along D to B. Y does change. Y progresses from 0 to 1. Y is equal to 0 at the point D, and then it increases until it reaches the value 1 at the point D. So these aspects of the behavior of x and y along the curve D to B, these are enough to evaluate the integral. So the integral, these are integration signs. The integral along D to B of L, and the integral along, sorry, the integral along D to B of this linear differential form, which we've written out a few times now. Yeah, it's 2y dy. But now we can make these substitutions. So the dx is equal to 0, so this term isn't going to, that first term isn't going to contribute anything because it's with respect to the differential dx, but x isn't changing, so dx is equal to 0. Look at the second part then. Okay, this is with respect to dy, so we won't cancel out for the same reason that the first term did. We've got an x here, but x we know is fixed at the value 1, so we can simply replace that by 1, so just get 3 plus 2y dy. And now, because it's only an integral with respect to the y variable, it's reduced to just a standard one-dimensional integral And so we can put in the limits for the only variable that's remaining there, which is the y variable. So this reduces again to something very familiar, just that integral with respect to y, which would be 3y plus y squared, evaluated in 0 and 1, which is going to come to 4. So the original integral along the curve C of L is now equal to the sum of these two parts. Okay, because remember we employed property 3 to say that the integral along the original curve C is equal to the integral along the curve A to D, and then plus the integral along the curve D to B. So we're just adding up the contributions 0 and 4, so we get a total value of 4. And the important thing to notice about that is 4 is not 5, which was the integral along the curve y equals x squared of the same differential form. This was, so one was integrating along this curve from the start point to the end point, and the other one was going along these two straight line segments. So integrating along those two curves, either going along y equals x squared or going along the two straight line segments, they give you different answers to the integral, even though they're going from the same start point to the same end. Okay. But that is really what we would have expected, because they're going through completely different points. I mean, apart from the start point to the end point, there's no other common points in the two curves. They're moving over different parts of the domain of these functions that are appearing in the linear differential form L. So really, it's no surprise really that the integrals come out as different. However, there is an important class of integrals where sometimes the linear differential form is particularly special. And it's special in the sense that it does have the same value no matter which curve between the start point and the end point you choose. Those are very special linear differential forms. They're called path invariant integrals. Phrase path invariant. Something like that. This is, yeah, path independence, path dependence, or path independence. These two examples, these two integrals of the same linear differential form L, this shows that L is path dependent. It depends on the value of the integral between this particular start point and end point. It depends on the path taken. Okay, let's just look at one more example, example 1.16, before we finish today. And this example illustrates another way that we can sometimes evaluate these integrals. But we haven't said much about what these integrals actually mean. We will look at an example or at an example application area or two in the next lecture. So there's one application about coming from the physics idea of the work done by a force when moving a particle and so on. And there's a couple of other application areas which I'll tell you about as well. But this example just illustrates another kind of evaluation technique. So here we're integrating along a certain curve C here, this linear differential form. And the curve C, we're told, is the semicircular path of radius 1 traversed clockwise from -1, 0 to 1, 0. Well, that's worth the diagram. So it's example 1.16. square those points. Minus 1, 0 to 1, 0. So it's going to be this point here to 1, 0 here. Semicircular path of radius 1 traverse clockwise. So we're talking about this path here. Let's do point 1 there again. So this is the curve C in the xy plane. And now you see, this isn't an example. So the best way to describe, well, maybe not the best way, but yeah, the best way to describe C here is not by, y equals some function of x, or x equals some function of y, but rather using a third parameter. Circles are not easy to describe in this y equals a function of x or x equals a function of y, right? And it's better to introduce a third parameter, which is like an angle, which is really this third parameter, although we're going to call it t like time, but really it's the polar angle. Think of the polar coordinate system that we introduced a few lectures ago. Well, last year, but in the polar coordinates in 2 dimensions, in the radius of a point and the polar angle, the angle made by the radius with the positive direction of the x-axis. If we introduce that polar angle, then the curve C will be parameterized by cosine and sine of that polar angle. Okay? So C is parameterized by functions. X is cosine of t, y is sine of t, and we want to go clockwise. So how's the parameter going to behave? Well, t is going to start from the value pi and go down to 0. We call it t here like times. This is kind of imagining the part. Well, yeah. If I was redoing this, I might call it theta as well, just to emphasize the connection with polar coordinates. So really should call t theta, just to accord with our previous use. But no matter anyway. So then using these parameterization functions, you then get similar expressions for the differentials. Again, using chain rule principle, the dy and dx will come out as functions of t and the differential dt. So then we have something to substitute for x and y, something to substitute for dx and dy, and after we do those substitutions, the whole thing comes out as just an integral all with respect to t. Okay, so that's developed in the rest of the example there in the notes, you can see it. So we start off with the original integral x squared dy minus y times x dx. We make all the substitutions there for x, y, the differentials dx and dy. And we can do some simplification because we see there's a factor of cosine squared plus sine squared there. It's just the previous terms, that's always equal to 1. So that can factor out, and the whole thing reduces to just a straightforward integral of cosine t dt. And note there, the way the limits of integration are put in, it's integrating from pi to 0. Because that's how the parameter evolves to trace out the curve C. Okay? So the starting value of t is pi, the ending value is 0. So you just have to take note of that order, see in the evaluations down in equation 155 there. And it turns out the whole thing comes out of 0 anyway. But, so that example just illustrates kind of another way that these things might be evaluated. When we have a parameterization of the curve using some third variable. Okay, we better leave it there for this morning. We shall continue exploring theory of integration then from next time. I'll go back to the screen in a moment.